Recording in progress.
All right. Good afternoon, everyone. We are going to be kind of reviewing chemical reactions and kind of building on what we already learned. So a lot of the stuff you probably have already seen and we discussed before, but we're going to learn new things. But we're going to remember that chemistry is very cumulative. So we're going to take what we've learned and keep building and building and building. So more on chemical reactions and aqueous solutions. If I say something is aqueous, does anyone remember what that means? So aqueous means that it's in water. So if I was to say aqueous solutions, it just means I'm taking the random chemicals and adding them to water. So if I was to take table salt and add it to water, now I have an aqueous solution where I just dissolve salt. It's aqueous. I have a quicker question. So I know that most students are online, but if you'd like to type it in the chat, I'd love to hear it. Which statement is the best description of your attitude towards balancing chemical equations? So we did this at the very end of unit 1. So A, it's easy. B, some are easy, some are hard. Or C, say what? Not easy at all. So what do you think? B. Okay, something easy. Anyone else want to? You don't have to, but I'd love to hear your opinion. Yeah, so I would say most students are probably around B. Some are easy, some are hard. But at least we discussed having those basics. So even if the equations start to become more and more hard, as long as we have those basics down, we are capable of getting the harder one. It just requires practice and getting comfortable. So let's just do some review. Most elements are very happy being by themselves. Like if I was to take these, iron Fe, it's just happy if you have pure iron. Sodium's happy by itself, although I'll tell you now, it's very, it'll react with water if you have pure metal sodium. Silicon, carbon graphite, very happy by itself. So I would say most atoms are happy being mono means one, monoatomic. But there are the 7 Brinkelhoff ones. So the halogens, bromine, iodine, chlorine, and fluorine, those are all going to want to be diatomics. Then you also have oxygen, hydrogen, and nitrogen. So Dr. Patterson recommends like just thinking Brinkelhoff. So when you spell it out, it looks like Brinkelhoff. Let's review. The past 2 days in class, we practiced naming ionic compounds. For these ones, you have to remember which ones are covalent versus ionic, because ionic compounds, you can use those charges to kind of estimate what are the names and things like that. So with ionic compounds, you have metal plus nonmetal. Or for those, that tricky one is if it's ions in solution. That was it with ammonia. Even though it looks covalent, it's not. It has ions. So write the cation with charge, write the anion with charge. Always start with that. If the charges cancel, you're done, like NaCl. They both have the same charge, even though it's negative and positive. They essentially will cancel out, and that way it's neutral. It's just going to be NaCl. But if it does not cancel out, like if I have, let's say, magnesium, those charges do not cancel out. So you have to use the crisscross method, where the 2 goes here, the 1 goes here, and you have magnesium chloride. So it's going to be very helpful for us to identify what are the charges, and you've gotten very comfortable figuring those out. We're a little new-ish with polyatomics, so give yourself some grace, but keep remembering and doing a few every day or looking at them to help you remember those charges. If you do have a polyatomic ion and there are more than one of them, you have to put in parentheses. So let me do that right here. Let me think of one. So if I have Al 3 plus and OH minus, I have to use the crisscross, and I now have Al, but I can't just do OH 3 because that's not the same thing as OH3. That's saying 3 hydrogen with 1 oxygen. I have to make sure the entire polyatomic ion is in parentheses. For covalent and molecular, we don't need to do that because it doesn't have charges. So you'll write the first element and then the second element, and you'll remember those prefixes like mono, di, tri, tetra. And then alkanes, I feel like we're the most comfortable with. So we just have to remember this little formula. So CnH2n plus 2. I would say by now, or at least make it a goal this week to finish your 2.1 homework. I should have quiz 3 up and ready by the end of the day. I'm having some computer issues in my office, but my goal is end of the day to have that up. But if you can do all of 2.1, and I would say start going through 2.2, and then potentially look at the quiz, maybe for at least the first one, because you get 2 attempts, that will make next week a little bit less stressful. Because I know my goal is for you not to have to worry about homeworks or quizzes the 2 days, the 48 hours before the next exam. I would say that would be a good goal, is to not have to think about homeworks and quizzes 48 hours. So if you can get all of that done before that 48-hour window where we're just going to focus on exam, that would be very helpful. But yeah, so 2.1 homework, definitely get that done. And then I just created 2.2 today. It is now open. And if we have downtime left over today, I'm going to open it and we're going to go through it together. So some of the questions are straightforward and easy. Some of them require a little bit of work. So start going through 22.2. And then next week we'll do 2.3, 2.4. Review, we have coefficients, what are the numbers out front. They tell you how many of a specific molecule you have. And subscripts tell you the elements that are on the molecule and how many of those. We do not play around with subscripts. If we do manipulations with chemical equations and balancing, we never touch the subscripts. So Dr. Patterson recommends putting a box around it until you are comfortable remembering that. And when we balance things, we only mess around with the coefficients. So if I look here, I have a bunch of water molecules. I can't just do H8O4 because that's not the same thing. That would be a completely different compound. So that's why we have to break it up and say I counted 4 individual H2O or molecules, so not atoms. I love this type of question. This one's a good challenge. This one says, how many oxygen atoms are in 5 aluminum, that's aluminum sulfates? Remember that we don't play around with prefixes. That's aluminum, which always has a 3+ charge, so I don't have to put the little Roman numerals in, and then sulfate. So this one's a great challenge because you need to figure out how many oxygens are in the molecule itself, but there are 5 of them. And when you have the answer, you can type it in the chat or just put it out. You got it? Yeah. So this one answer is going to be 60, and I'll show you. Yes. So I have 3 separate sulfates attached to these aluminums, 3 of them. So I have to multiply the 3 by 4. So in each individual aluminum sulfate, I have 12 atoms of oxygen, but there are 5 of them. So 5 times 12 is 60. So this goes back to what we were doing in dimensional analysis. So I might ask you to do this now. I'm going to ignore the 5 real quick, but we're going to do equivalence. This is all getting you ready to do equivalence. So ignore the 5, but for every 1 molecule of Al2, SO4, 3, I have how many aluminums? 2. 2 atoms, aluminum. How many sulfurs? So it's in parentheses, and there are 3 of them. So I have to multiply the 1 by 3. 3 atoms of sulfur, and then we have 12 atoms. So this is kind of getting us ready for if I was to start doing dimensional analysis with these harder compounds, you can still use what we learned in dimensional analysis to figure out what are those equivalents. And in this case, I wouldn't need the 5 because I'm trying to break down the individuals. It's 2 separate things. But if I need to count everything, if there's a number out front, you have to incorporate it. So continue reviewing. I do want to point out that this course builds. Our goal is to keep looking at things over and over and over again so it sticks with us. So when we hit Gen Chem 1, or if you're taking engineering chem, it's still fresh in your mind, because if we were to learn something for a day and then never see it again, we're probably going to forget it. So yes, a lot of these slides are redundant, but we are going to build. So let's do a little bit of review for combustion reactions. What is required? What element is required for every combustion reaction? Yes. No matter what your fuel is, it could be a metal, it could be a covalent compound, you always need oxygen to create a combustion reaction. And oxygen will always be in those reactants. Sorry, that's products. So oxygen will split and combine with your fuel to create your products. Okay, so we have CH4 plus 2 oxygen plus CO2 plus 2 H2O. So they already balanced it. And so if I was to count everything out, there's a 1 carbon on each side, there are 4 hydrogens on each side, and there are 4 oxygens on each side. So they are already balanced. So this would be a good one. Like, if I wasn't to give you those numbers, can you balance them? Continuing the review, with chemical reactions, a lot of things can be given from what we give you. So first, I can give you the identity of the reactants and the products. So I can give you, A plus B becomes AB. So I'm giving you what are the elements, what are the compounds involved. I can also give you coefficients. Coefficients are the numbers that are up front. So if I had so I have 2 out front here and I have 2 out front here. So I just balanced that real quick. This is how you can create water, or go from water and use water to separate it and create hydrogen and pure oxygen gas, which is a very popular reaction. Oh, that's so ugly. Sorry, put 2 out here. So the coefficients are important. It tells you how many of each of them. In this balanced reaction, I would need 2 hydrogens plus 1 oxygen to create water, and there would be 2 of them. The physical states. So sometimes we'll start incorporating what the physical state, so solid, liquid, or gas. And aqueous is what we add to represent that it is dissolved in a liquid water. So it's the same thing as saying it's a liquid, but in this case, the liquid is water. So I guess I can do something like that. So previously, with that combustion reaction, you had CH4, which is usually methane as a gas at room temperature. If I mix it with 2 oxygen, that oxygen's in the air, it's a gas. It explodes and it produces CO2 gas, and then it also produces water as a gas. That kind of tells you of what's going on. If I was to replace those gases with something else, I can replace it with solid, liquids, or aqueous. So for aqueous, a very popular one is this. NaCl, table salt, is a solid when it's by itself. If I was to take that table salt and dissolve it in water, it's now a liquid, but that aqueous tells me that I dissolved it in water. So I don't need to write this as NaCl plus H2O. I'm kind of saving myself time here because I know I dissolved it in water by simply just doing table salt the solid and then NaCl aqueous. So I'm not asking you to do this now. I'm just showing you I can learn so much by what they are putting in these reactions. And lastly, when you get into higher up chemistry, they can tell you more. So they can tell you, are they adding heat? So sometimes they'll add heat as a reactant, or sometimes heat is produced, like a combustion reaction. Heat is definitely a product of a combustion reaction, explodes. So you can actually add in that as a reactant or a product. Light could be something that's added in. If you were to, create a reaction based on light. I know there are so many reactions that if I add light over time, it'll cause whatever beautiful color reaction I made, it'll clear it out. It's awesome, but not so awesome if you're wanting to do something without light. Solvent, it'll tell you about what your solvents are. So, aqueous is the most popular because the solvent's typically water, but here they have a solvent that's ether. So it'll tell you a lot. This is more organic chemistry. Catalysts and reagents. So it's really nice to be able to understand all the information they are giving you in these balanced reactions. This is just review what we did in unit 1.7. So I'll go over that again, and we want to just make sure we're getting more and more comfortable doing this. So balanced equations. Sometimes they're nice. I would say for most exams, I would give you the balance, or I would give you the products and reactants and say balance it, just like what you did in exam 1. Not so bad, but sometimes they're not so nice. They might spell out what's going on, and you'll have to be like, okay, well, I know how to name compounds. I can take those names and create that balanced reaction. So write out the formulas for all the reactants and products separated by plus signs or an arrow. And this is when you need to write in those subscripts. Then you pick an element and you start balancing the coefficients on each side so those elements are equal on both sides. My advice is start with, do not start with pure elements because they're the ones that you want to do last. So I always kind of start with like the bigger compounds and then I go, with the smaller ones later. And here's a very important new tidbit. Keep polyatomic ions the same, because if you start separating out, let's say SO4 2 minus, and you start doing the sulfurs and the oxygens, that might not be as easy. But if you say, okay, I have SO4, I have one on this side and one on this side, that will save you so much time and effort, is keep them as a unit. And we'll do a lot of examples of that. Repeat until everything is balanced. I have some practice problems in the homework. All right, let's practice. This is a great example of how we have to remember what the namings of everything is, and we have to remember what our polyatomic is. So it's not so nice, but we are capable. Silver is Ag. Does anyone remember what the charge of silver is? +1. Silver will always be +1. So you really want to have those charges there because sometimes you need to crisscross. This is how you can get those coefficients if they're not provided. So silver is a +1, and then nitrate. Do you remember what nitrate is? Oh, I just gave it shit. It's NO3, and it's a -1 charge. So that means I don't have to add any coefficients here. I can leave it as is. So silver nitrate reacts, I'll do a plus sign, with barium. What is the charge of barium? +2. And then chloride charge. This one will require coefficients. That's why it's important for us to remember that crisscross, and that means that we have now 3 plus BaCl2. All right, and it produces Ag plus Cl minus, so silver chloride. We do not need to crisscross that one. And barium nitrate. This one also needs a crisscross. So the 2 will go here and the 1 will go here. Don't forget the nitrate needs to be in parentheses. So now it took a little bit of work because we need to make sure that our subscripts are correct. But the next step is now we can balance. So you want to go and count the elements, I'll just write down the elements underneath, but I'm not going to separate the NO3. I'm keeping it all as one unit because I want to save myself time and effort. So I'll do NO3. We're about to balance. That's a great question. Where did the 2 from chlorine go? We have to balance it. But we don't put a 2 after this one. This one does not have a 2 because here and here, Ag and Cl will cancel out. This one does not require a crisscross. Ba and Cl. So let's count everything. How many silvers? Both sides. 1 and 1. Yeah. I'm just looking at the Ag and the Ag. How many nitrates on the left side? How many on the right side? Barium, 1 and 1, and then chlorine, 2 and 1. So we need to figure out, we need to get the chlorines to match, and we need to get those nitrates to match. So everything else is the same. So first, I'm going to start with the nitrate here. So for me to balance that out, I need to put a 2 in front of the silver nitrate. So now I have 2 nitrates and I have 2 silvers. The last thing I need to do is put a 2 in front of the silver chloride to get 2 silvers and 2 chlorides. And so now everything is balanced by adding those 2. So be patient with yourself. First, make sure your subscripts are correct. And then once everything is correct, you can start balancing. So this is like a 2-step one versus if I was to just give you the reaction. But it's doable based on everything we've learned so far. Any questions on that? What is the sum of the coefficients of the balanced equation when silver nitrate reacts with barium chloride? This is a great way for Dr. Patterson to ask this question on an exam, because if this was a homework, it's easy to just Google it and just get the answer. But this one, you're not going to be able to get on Google. So you have to be able to count everything up. So let me rewrite this since I don't expect it memorized. Count up those coefficients. So I had 2 plus 1, and then 2 plus 1. So 6. Did y'all get 6? Yeah. So it's a good challenge to make sure like you have the correct coefficients. So pro tip review. Occasionally, as you go back and forth on these coefficients, you will end up with a set of coefficients that could be reduced. Reduce them. That would be like if all of the numbers were like 2s and 4s, you can reduce them to 1s and 2s. But that means that every number can be divided by the same number. Yeah. Otherwise, your equation is not considered correctly balanced if you don't reduce. Okay, let's keep practicing. These are good. So we're remembering a lot of stuff. So I'm going to do sodium plus, because we know sodium is a +1. Does anyone remember what phosphate's charge is? 3 minus. This one will require a crisscross. I'm doing it up here so I have more room under. So that would mean I would have Na3PO4. So that is the correct sodium phosphate. And that's the name. We don't play around with anything else. Sodium phosphate. Reacts with barium chloride. We just did barium chloride. We also need to crisscross that one, just to review. To make barium phosphate. That's Ba2 plus and PO4 3 minus. That one will also require a crisscross. And I have to keep that unit or that polyatomic anion in parentheses. And then sodium chloride. That one, pretty straightforward. Na plus, Cl minus, they cancel out. It does not need crisscross. So we've double checked. All of the subscripts are correct. We can start balancing. So I have sodium. I have phosphate, which I'm going to keep together. I'm not going to break up the P and the O's. I have barium and chlorine. So if I count on the left side, I have 3 sodium. On the right hand side, I have 1. Phosphorus, I have 1. Right side, I have 2. Barium, I have 1 and then 3. Chlorine, I have 2 and 1. The first thing I'm going to do is probably balance out the sodiums because that's the first thing I'm seeing. If I put a 3 out front of that sodium, I now have a 3 here and a 3 here, which might get a little complicated because it's very hard to add that extra in a blend. Usually you want it to be even. So we might have to play around with that number a little later on. But at least our sodium is balanced. The next thing I'm going to do is I have 2 phosphates here. So I'm going to put a 2 out front over here. That's probably going to affect what this number here on the right hand side. So by doing that, I now have 6 sodiums and 2 phosphates. So that's probably, maybe I would have started, if I started with that, I could save myself time, but it's okay to, figure things out as we go. I'm going to erase this 3 real quick because now, since I have 6 sodiums here, I'm going to put a 6. So that is going to be so much easier for us to balance out those chlorines since I don't have an even and an odd. So barium's next. I need to put a 3 out front of the barium. That gives me 3 bariums, and 3 times 2 is 6. So just checking, 6 and 6, 2 and 2, 3 and 3, 6 and 6, which means we are all balanced. But this took a little bit extra time, and that's okay. Just play around with those numbers and try your best to like double check everything before you move on. Does everyone agree with me? Does this look right? I'm going to let you all do this one, but let's break it up. We have ammonium nitrate. Does anyone remember what ammonium is? Okay. It's NH4 plus. If it was ammonia, it would just be NH3. So ammonium is NH4 plus. Nitrate is NO3 minus. So ammonium nitrate decomposes to make nitrogen gas. What does that look like? Yes, N2. Let me get some more space. What about oxygen gas? O2. And then lastly, water. So to balance this one out, we need to put nitrogen, this case, we cannot keep the polyatomic bond together because I don't have ammonia on both sides and I don't have nitrate on both sides. So this was the only case where we'd have to break it up into the elements. Y'all take a crack at it, see if you can balance this. So 3 NO3, I don't believe it is. If I was to do that here, it would be 2NO3 is equal to NO3, 2. Yes, because it would be over here, I'd have 2 nitrogens and 6 oxygens. Over here, I would have 2 nitrogens and 6 oxygens. So yeah, it would be the same here if the way that I wrote it on the top right. This one's a little tricky. The way that it's balanced out right now, the only thing I need to really mess around with is hydrogens. If I was to like put a 2 out front here, I now have 4 hydrogens, but it messes up my oxygen. So now I would have 4 oxygen. It's more difficult. So the only way to fix that is I'd have to put a 2 out front here, and that will change everything. So this one just is a little challenging, and that's okay. So it's going to take some trial and error. So if I put that 2 out front of here, now I have 4. Actually, I can leave it like this. It's a little messy, but I'll have 4 nitrogen. Let me know. I'm going to pick different colors. I have 4 nitrogen. I now have 8 hydrogen. And I have 6 oxygen. So for me to combat that over here, I need to erase this 2 and replace it. So I want 8 hydrogen. I'm going to put a 4 out here. And that gives me 8 hydrogen. And that gives me 4 oxygen plus 2 is 6. So the last thing I will need to do is put a 2 out front of the nitrogen to get 4. So it took a little trial and error, but we were capable. This one, you cannot divide it all by 2 because there is a 1 out front of that oxygen. So if you were to divide everything by 2, that oxygen would be like a 1/2. That's okay, but typically we want to keep it as whole numbers. But did y'all see how I was able to get that? Does anyone need me to repeat anything? Yeah, be patient with yourselves and just use the trial and error and try to like, start with the top ones, and then move your way down. But like I said, I did the pure element last because that was the easiest thing to fix. If I did that pure element first, it would mess everything up. So patterns. Much of chemistry is about identifying patterns. In the series of generic reactions on the next slide, what patterns do you see? How do you describe these patterns in words? So I love that words tell us a lot about the reaction. There are some patterns you can develop, like if I was to say the word decomposition, if you look at this equation, can you see why decomposition would be a correct word for that? Because it is having a solid compound and breaking up into individual elements, pure elements, so it's decomposing. So if I go back to some of these questions, ammonium nitrate decomposes, so it breaks up. So it kind of tells you about the type of reaction. So then it's breaking up into individual pure components. Not always pure, because we still have water, but you do have pure components there. So it tells you a lot about the reaction. Synthesis is when you have elements and you combine it together to create a compound. Single displacement. So I have A plus BC, and then what happens is something here will split up and join the other thing. So it's one thing is being shifted and combining with another thing. That's single displacement. Double displacement, it means you have both of your reactants will break up and attach to the other one. So you have A, B, and C, D. So A will combine with D, B will combine with C. How do I know that? We're assuming that A and C are cations, B and D are anions. So it's, of course, you need to have a positive and a negative charge to create that ionic compound. So they split up and then they attach to the opposite component. So it's double displacement. And then the one that you're probably most familiar with so far would be combustion. Some type of fuel is combined with oxygen and it creates products that have oxygen in it. So synthesis, two things come together to create something. Decomposition, something breaks up to create pure elements. Single displacement, one thing is switching. Double displacement, everything is switching. Combustion, fuel plus oxygen. Okay. Let us identify. For me, if I see this, I'm a little overwhelmed. So I would probably go through and probably pick the easiest ones, but let's just do one at a time. Let's do number 1. I have 2As2S3 and oxygen. What type of reaction is this? Remember, what is the definition or what is required for a combustion reaction? Oxygen, right? And oxygen has to be in both of the products. So to me, to be honest, when I look at this, I'm thinking in my head, is this a single displacement? I don't know. But in reality, this is a combustion reaction because I have a fuel plus oxygen and it creates products with oxygen. This is a combustion reaction. This is a tricky one.
Not all combustions are going to contain CO2 in H2O.
No, but so this is an example of like a question I can continue to keep asking. If I was to throw in metals, it's just going to be something plus O2 creates products that incorporate oxygen. That's tricky. The next one, Na and Cl becomes NaCl. This is a synthesis. That two pure things combine to create a compound, so synthesis reaction. Let's do the calcium. Ooh, let's name this. What is this name? Yeah, really straightforward. Ionic compounds are pretty straightforward. So calcium hydroxide. What's the next name? Aluminum sulfate. So I've had calcium hydroxide and aluminum sulfate, and it produces calcium sulfate and aluminum hydroxide. What type of reaction is this? This is double displacement. So even if you don't really know on top of your head, you can always eliminate what makes no sense. It's not combustion, it's not synthesis, and it's not decomposition. It's either single or double. But when I look really into it, it all flipped around. Everything flipped. That means it is double displacement. I don't have a lot of space, so I can't write it out. So double displacement. All right, the next one, we have lead sulfate produces lead, I think that's sulfite or something. I don't have that memorized. Plus oxygen. What type of reaction is this? Yes, this is not combustion because it's not introducing O2 in there, even though there's oxygen in both products. It's not, there's no O2, it's not a combustion reaction. This is a decomposition. We have a pure compound that separates into we have a compound that separates into more pure or multiple things. So this is decomposition. H2O plus SO3 becomes, that is sulfuric acid. What do y'all think this is?
This would be synthesis.
Yes, this is not single displacement. This would be a synthesis. But yeah, but when in doubt, kind of go through the list and say, what is it not? All right, we have HCl plus NaOH, that's hydrochloric acid plus sodium hydroxide produces sodium chloride and water. Yeah, this is double displacement. And lastly, I have propane and oxygen creates carbon dioxide and water. Combustion. Yeah, you just didn't have single displacement here. I think this one, I think I got tricked in my notes and I said this was single displacement. This one could probably be both single displacement or combustion, but I think when you get some chemistry questions, multiple choice, it's which one is the most correct, and I believe this one is most correct as combustion. Yeah, I have some more questions like this in the homework that are quicker to do. They look like this. So I have a question and I have a reaction. It's balanced and it says what type of reaction is this? If you want to answer it in the chat or just say it out loud, you're welcome to. Not synthesis. Definitely not combustion. It's not double displacement. That's B or C. I saw the answer in the chat. Do you think it's B? Yeah, I agree. It's B. It's not single displacement either. So this is a decomposition reaction. Great job. What about this one? Definitely not combustion. Yeah, this one I would eliminate A, B, and E. And it can't be double displacement because you have something that's by itself right here, but it's not splitting up. So that would have to be C. This is single displacement. Yeah, I have very similar questions like this in the homework where I'll give you a reaction and you just got to figure it out. So don't just guess until you get the right answer. I know it's easy to do that when you're panicked on the homework, but really think it through and really challenge yourself. What type of reaction is it? So far, our description of chemical reactions has been mostly symbolic, but let's look what happens at the particle level for many reactions in aqueous solutions. And I do have a PhET simulation I would like to show y'all. Okay, so most molecular compounds in water, that is a most because some molecular compounds will break up into ions, and that would just be acids and bases, but we're not there yet. So most molecular compounds, covalent, non-metal plus non-metal. They can dissolve in water. So they're not going to just hit water and stay as a solid. If I take sugar, sugar is a molecular compound. It's just carbons, hydrogens, and oxygens. It is molecular and covalent. When it hits water, what happens at the microscopic level is it breaks up into its pure component, but it's not breaking up into ions, whereas ionic compounds will. So if I was to take a clump of sugar and add it in, it just breaks up into individual compounds of sugar. So it does not break up into ions. So if I was to dissolve ethanol in water, you still have pure ethanol molecules in there. It doesn't break up into carbons, hydrogens, and oxygens. And typically students will confuse this a lot and they will try to break this up. But if it's not an ion, the only ion here is OH, but it's not going to break up because everything else is not an ion. So I want to show y'all what I mean by that. Okay. I love PhET simulations. If you ever, sorry, it's just behind this. I hate that this doesn't move. Like, how do I move this? Oh, I could move it. Okay. Okay. Here's a PhET simulation. Can everyone see this? All right. Sucrose or sugar is something that is a molecule that easily dissolves in water. If I was to, and I love this top left here because I have micro, macro, and water. On the macroscopic scale, if I was to just add a bunch of sugar to water, It dissolves. It dissolves in water. So, but we're not really seeing what's on the particle level. So let's add some sugar. These are clumps of sugar as a solid. I don't know why. Oh, there it goes. So what's happening is it's dissolving. It's just taking that big clump of millions of sucrose compound or molecules, and it's breaking up into individual sucrose molecules. But notice how it is not breaking up into ions. So it's staying as a full unit, full sucrose. That is because it's not ionic. It doesn't have ions. Now, the last one in the top here, these are water molecules. And if I was to add, this is, let's say this is a clump of sugar. The water molecules just rip it apart, but it doesn't rip it up into ions. So it's still a full sucrose unit. This will happen with most molecular compounds, with the exceptions of acids and bases. But they stay together. So I don't want, if you see a molecular compound and I say like what happens when you add it to water, I don't want you to like say, okay, I have carbon 4 minuses and hydrogen pluses and oxygen 2 minuses. No, it stays together. It just is now aqueous. This is when you go from sugar, from solid to aqueous. Ionic compounds, salt, NaCl. If I add it to water, it's the same thing. It's going to dissolve in water just as well as it does with sugar. But microscopically, let me reset. Microscopically, what's happening? So I have a solid NaCl. Because it's ionic, it's a metal and a non-metal, it breaks up into its ions. So I have Na pluses and I have Cl minuses now floating in water. This is also why electrolytes are so nice, because we have a lot of that in our drinks. This is an example of that. So you have ions that our bodies need. Yeah, that's what's happening microscopically. If I want to show you how the water affects it, it's the same thing. This is a solid piece of NaCl, but the water causes the ions to break off. I love this simulation. I use it with all my gen chems. But yeah, this just helps us visualize. As a visual learner myself, this just helps me visualize versus me showing you a slide. But yeah, honestly, if you ever want to play around with it, just Google PhET simulation, PhET simulation. When I was going through, like, I wanted to show you how many they have. I just Googled PhET simulation. And this could be helpful for all your classes. If you have physics, math and statistics, or chemistry, pretty much anything that we're working on, I can go through. So a lot of these are like upper levels, but they have more basics. So like if you want to do the pH scale, if you want to do shaping, which we might do later, I have another one for balancing chemical reactions. So we have some time. So this is another PhET simulation that goes over balancing, and it helps us visualize. So I have ammonia here, and they all have 0. I'm going to start by having one of everything. Is it balanced? No. Because I have 1 nitrogen here and 2 nitrogen here. So I'm going to start by changing that to a 2. Is it balanced? So I have 6 oxygen over here. Oh, wait, sorry. 6 hydrogen over here and only 2 over here. So if I do it like that, oh, it's balanced. That's one way we can visualize it. They have another way right here. I'm going to do separate water. Okay, so I'm going to do 1s for everything. And I like how it's a scale. It's showing me the hydrogens are balanced, but the oxygens are not. So I'm going to come over here and balance the oxygens, but now our hydrogens are not balanced. So if I, yay, now it's balanced. So they have a bunch of different ways. If I try it this method, let's do combustion. 1s, 1s, 1s. I'm just going to finish this and we'll start our break. 1. Okay. So it's saying our hydrogens are not balanced. So if I was to like up my hydrogen count, the balance, carbons are balanced, but our oxygens are not balanced. Oh, now it's balanced. I love this. And so if you really want to challenge yourself, they have a none option where you don't have the visual aid. But if you're a visual learner like myself, this is a great tool to help you. I just wish they had more reactions. Like I wish they had a bunch more options. They have oh, they do. They have equations. Is it balanced? No. Okay. Got 2 oxygens, 2 carbons. I need 2. Yeah. Okay. So it does have other things you can play around with. Decomposition, combustion, and then they have a game. Oh my gosh. So you can play around as you're learning reactions. If you really are a visual learner like myself, I'm sorry, I love to do this stuff for fun. So this is a great way to do it. All I did was just Google PhET simulations, and then I found the balancing chemical reactions one. Yeah, really good practice. Yeah. All right, so it is now 12:51. Let's come back at 12:56 and continue everything else. Okay, so going back to the slides, if it's a molecular compound, so it's covalent, it's all nonmetals, they dissolve as a whole unit, they are no charges, and this is an example of a non-electrolyte. So I think most of us have heard electrolytes in our lives, and I know like if you like to work out, you need to definitely have electrolytes in your system or you cramp. I am an avid tennis player and I cramp all the time, and yeah. So these compounds, ethanol is great if you're above 21, but it's not going to help you with your body. But what happens in solution is it just stays as a whole unit. Also, never drink 100% ethanol that's used for like medicinal or lab stuff. I always have to tell students don't drink it. If it's a lab related stuff, it'll kill you. Okay, ionic compounds. So metal plus non-metal. They separate into ions because they have those charges, with the exception of if you have like NH4Cl. That there is no metals in this, but NH4 is a plus and chlorine is a minus. So when it hits water, it also will break up into ions. So another exception if it's like acids and bases, they are also electrolytes. So electrolytes are ionic compounds. When they hit water, let me go back one slide. I want to show y'all, if I was to have ethanol, CH3CH2OH, at room temperature, it's a liquid. But if I dissolve it in water, like I have in this picture, the way that I would write it would be CH3CH2OH aqueous. So this reaction that I just wrote out is me kind of telling you I've now taken pure ethanol and dissolved it in water without me having to include water molecules in my reaction. Over here, let's say this is NaCl. I have NaCl, and it's a solid right here. This is a solid. And if I dissolve it into water, what's happening is it breaks up into ions, but I still have to put it aqueous because it's still a liquid. So this is microscopic, but what I just did on the past two slides is I showed you the symbolic version of what is happening. So it's good to think of it in both. I think it's harder to think of it in macro because it's just dissolving in water, but microscopically it breaks up into ions, and then symbolically you have the balance reaction. So it breaks up into those ions, so Na plus and Cl minus. Okay. These are electrolytes. Electrolytes are compounds that conduct electricity. So if I was to have an electrolyte solution, and then you can take an ohm meter and you can add, those little things to it, and it'll show you if it has the ability, to have a circuit, and that would be, it's showing you there's electrolytes in solution. If I was to take that same meter and did it into sugar water, nothing would happen, nothing would read. You're gonna actually be doing a lab with me when you take, it's fun. I wrote a lab on conductivity where we do a full lab of analyzing different solutions conductivity. So I don't know when you're gonna take 1135, but you'll do in the fall, you'll be doing a full lab. So that's lab 3. So compounds that conduct electricity when liquid or when dissolved in solution. So ions are electrical conductors, not electrons in solution. So these are just the ions. If you have the positive and negative electrode, you'll see a charge. A really fun way we used to do this, but it's harder. We used to do light bulbs in lab. It's just harder for us to do it nowadays because the light bulbs the batteries went out. But let me see, I had this really fun PhET simulation. Let me see if I can get it up. I think I have to Google it. That's not it. Should have had this one up, I'm sorry. No, connectivity. Bunch of sugars and salts. No. Go back here. Sorry, there's this one PhET simulation that I love to do. It also does sugar and salt with a light bulb. Yeah, that one. Yes, that one. Okay. Yeah. Okay, I'm coming. Sorry. Sorry, I'm such a visual learner that like it's just hard when you're online, and I can't do like demonstrations. So salt, table salt, NaCl is ionic, and so when I add it to water, a bunch of it, the more you have because you're having more connectivity. If I add a light bulb, the more I add, it should get brighter and brighter and brighter. You see how the light bulb is getting bigger? So yeah, the more and more and more ions you have in solution, the more connectivity is, the more electrolytes. If I was to reset this with sugar, no matter how much sugar I add, the light bulb will never turn on because it's not not conductive. It doesn't turn into ions. If I do the microscopic, which I prefer because I like to visualize, where's the light bulb? There's no light bulb. I don't know where. Yeah, I want to see the light bulb. No, look, no light bulb. Okay. Yeah. We'll just do macroscopic then. But yeah, this is another good visualization about electrolytes, what happens when it hits solution. Let's go back to the slides. Okay, sorry. So once again, compounds that conduct electricity when liquid or when dissolved in solvent. So they have to have ions to be conductive to be considered an electrolyte. So here's just a table that shows you different types of electrolytes. We start to think sometimes there are versions of electrolytes. Not every electrolyte is going to be very strong. Strong ones are sodium chloride is a very strong one. It means it 100% dissociates in water. They have weaker electrolytes, meaning that it partially dissociates, and then they have non-electrolytes. So everything molecular that has a covalent molecular bond will be a non-electrolyte. Will have no light bulb. Weaker electrolytes are things that are less soluble in water. If it's not as soluble, it's not going to be able to have as much ions in solution. But if it's like really, really soluble, that's when you know, okay, it's turning into all these ions, and that's why it's a stronger electrolyte. Acids and bases. So I say these acids, these look like they would be covalent bonds, but hydrogen kind of acts like a column 1 metal. So hydrogen has a +1 charge. That's why it's written above column 1. So if I was to put an H on any of these, it would also act as an electrolyte. All right. Electrolytes and dissociation. So remember, more ions means more conductive and the stronger the electrolyte. So if I was to keep all of these concentrations the same, let's assume they're all the same amount in solution. In this first one, we have a lot more positive and negative charges than we do in this one. So in this one, it looks like this thing didn't completely dissolve or break up into its ions. So this one, if I had a light bulb, the first one, it would be much brighter, much more bright because it has more electrolytes, it's more conductive. The middle one, some of it has turned into ions, but not all of it, and that's a solubility issue. And then the last one, we have no positive and negative charges. Therefore, it is not conductive and yeah, there are no ions. So dissociation is sometimes you'll hear me say it. kind of talks about how many ions are in solution. So if I say 100% dissociated and I had NaCl, that means that if I added NaCl into solution, 100% of it would break up into Na plus and Cl minus, 100%. That's why it's a strong electrolyte. If it's a weak electrolyte, I think calcium, anything with carbonate in it, let's use CaCO3. If I add that to water, only some of it will turn into calcium and some of it will turn into carbonate, but most of it will remain as a calcium carbonate. It just doesn't dissolve very well. There are ways you can get it to dissolve, but it just doesn't want to. So yes, some of it will be Ca2 plus, some of it will be CO3 minus, but majority will remain as calcium carbonate. And that's why it's considered a weak electrolyte. And you would analyze this in lab by, putting a conductivity probe in there and measuring. Lastly, if I was to do any molecular, nothing. Let's practice. The first thing you want to do when we start asking about these types of problems is understanding which one's molecular versus covalent. Molecular covalent versus ionic. So if there are metal plus non-metal and ions are present, it will definitely dissociate. So let's think about this microscopically and see what's going on. Show the substances starting as a solid or aqueous and ending with all the ions that form when the substance dissociates or breaks up into water. Let's say we're dissolving it into water. So we have barium chloride and it's solid. So if I dissolve that into water, what do I get? So I have Ba, what is the charge? 2 plus or plus 2, and I'm going to put an aqueous to let us know it is dissolved in water. What about chlorine? Is this balanced? What do I have to do to balance it? I'm going to put a 2 in front of the Cl because I have a 2 right here. So now we have the ions with the correct charges, but it's also balanced. You want to make sure you're doing both. All right, barium nitrate. So we have barium again. What do you do with a dead chemist? What do you do with a dead chemist? You bury him. Yeah. Is this balanced? No. I'm going to put a 2 up front of the NO3 minus because now I have 2 on the left side. I'm going to have 2 on the right side. So our ions are correct with the charges and it's also balanced. You want to do both. So once again, I do not want to put water on both sides, even if I am dissolving it in water and it is a part of the reaction. It's just a solvent. It's just what we're dissolving things into. It's not affecting, it's not affecting the reaction at all. So we tend to incorporate water by having it be aqueous. So if I take a solid and I dissolve it in water and it breaks up into ions, I put aqueous behind it to let me know that it's dissolved in water. So we're now going to get into different types of reactions. This is the double displacement or single displacement. These are fun. It's like, okay, if I add these 2 chemicals together, what happens? So what will happen when I mix 2 chemicals? And this is a great reaction because this is creating a solid. Do you see that? Yes, it is in a liquid, but what happens is in this case, I added 2 chemicals together and it creates precipitate or solid. It's precipitating out. Yeah, let's look into that. Solubility rules. If you came in person, there was some solubility rules just because I'm about to show you soon. I don't want to have you memorize the slide and have a slide up front. Oh, I'm myself. But what I did was I went in and I just Googled solubility rules worksheets or just an easy sheet. So it's in resources just because it's just good helpful while you're learning. So solubility rules. These are guidelines to predict if a compound will dissolve in water or not. Some things, like I'll give you an example. If I want to make sweet tea and I want my sweet tea, which I actually hate this. I don't like sweet tea even though I'm Southern. But I want my sweet tea ridiculously sweet. From my roots in New Orleans, we like our sweet tea super, super sweet. But unfortunately, if I have room temperature water and I add pounds of sugar, it's not going to dissolve. Why? Not all of it, at least. And that's because sugar is not as soluble as something like salt. I can get a lot of salt to dissolve in water, like seawater. There's so much salt in our seawater. The Red Sea, things like that, the Dead Sea, so much salt can be dissolved. But sugar cannot. So if I want to make really good sweet tea, but I can't get my sugar to dissolve, what do? You heat it up. By heating it up, you create a better solution and you allow it to be more soluble. At higher temperatures, that solid can dissolve easier. That is the most relatable thing I can give you about how solubility works. If it doesn't completely dissolve, we typically will heat it up. So these are guidelines to predict if a compound will dissolve in water or not. Sometimes some of it will dissolve, but not all of it. So most important ones are to remember that compounds containing nitrates, acetates, chlorates, perchlorates, ammonia, and alkali metals, so column 1, they're always soluble. Sodium chloride, sodium iodide, sodium bromide, potassium iodide, column 1. And so this little sheet here, the next slide also has those rules. So I'll show you here. So you don't have to like download the slides if you don't want to. That's why I have this little sheet. It's the same thing. If it involves any of that, it's always going to dissolve in water. But there are some exceptions. So I'll go to the next slide. So these are the ones that no matter what you do, if I do it with any metal, you know, let's do chromium nitrate, it'll always dissolve in water. It's always soluble, and there are no exceptions. If I did ammonia iodide, always dissolvable. So no matter what I throw at you, if you have that in front of you, you'll know it's soluble. Some things, fluorides and bromides and iodides, typically will be soluble most of the time, with the exception of 3 different metals. Silver chloride, not very soluble. It'll always precipitate out. So that's, let's say, when it says that X here, and I'm replacing it with like a chlorine, a bromine, or an iodine. So AgCl or Ag iodide or AgBr, something like that. So you're just taking that X and replacing it with one of those chlorides, bromides, or iodide. So they're usually soluble, except when they're combined with those 3 metals, silver, lead, or mercury. Sulfates are also usually soluble, with the exception of when they're combined with barium, lead, mercury, calcium, and silver. Hydroxides they tend to be insoluble. It's pretty. So if I was to take like the copper hydroxide, it's beautiful and blue, but it's very insoluble. It's going to be a metal. But they can become soluble if I was to replace the copper with like ammonia or column 1 metals and barium. Carbonates are also, they tend to be more insoluble. These are probably weaker electrolytes, with the exception of when they're column 1, when they're combined with column 1 or ammonia. I don't expect these completely to be memorized, but let's say on the exam or quiz, I gave you these rules. Could you figure things out? So let's play around and trying to figure things out. If you are online, I would just get this downloaded and have it next to you. If you have the slides next to you, you can also do that. Soluble or insoluble? So this is, like I said, I don't expect you to have this memorized yet. So have those rules next to you. Sodium phosphate. Phosphates. If I go here, compounds with these ions are insoluble, except when they are combined with alkali metals, so column 1. Is sodium a column 1 metal? So even though phosphates are insoluble, when it's combined with sodium, it's soluble. Do you see how I was able to deduce that? Okay. Magnesium sulfate. So I find the sulfate ion, and these compounds are usually soluble with the exceptions of when combined with silver, calcium, strontium, barium, mercury, or lead. None of them are magnesium, therefore this is soluble. silver sulfide. What do you think? So on here, at the very bottom, it says sulfides are insoluble except when combined with these elements. Silver is not in the exception column, therefore it is insoluble. Do you see how I was able to do that? Did y'all agree? The next one is lead acetate. What do you think? Soluble? Yeah. Anything with acetate, and there are no exceptions to the rules, are always going to be soluble. Last one is calcium carbonate. So carbonates are insoluble with the exception of column 1 metals. Is calcium column 1? No, it's column 2. Therefore, this falls under the always insoluble.
Yeah.
Cesium? Oh my goodness. You should research column 1 metals when they're added to water. So if I took a puck of pure sodium metal and threw it in water, it explodes. But as you go down, the explosions get bigger. So if you take a puck of cesium pure metal, oh my gosh, it's huge, huge. Yeah. So like I said, have this with you as you're going through these types of ones. It'll really help you because I still struggle having things memorized. But these are very, very helpful. Let's continue practicing. We have sodium acetate. What do you think? Acetate, yeah. I'm sorry, I jumped the gun. Acetate is always soluble, regardless of what metal you throw with it, always soluble. Lead phosphate. What is it? Yeah, so phosphates are under always insoluble, and lead is not one of those exceptions to the rule, therefore this is insoluble. Precipitation reactions. So what happens here is I'll have two soluble compounds, and if I add them together, sometimes it'll create an insoluble compound, and that's a precipitate reaction. So it's creating a solid, and that was this picture here. Go back. Go back. I had two liquids that are soluble, but when I add them together, it creates a solid. That's precipitate. So these are precipitate reactions. They're really fun to do in lab. These are typically double displacement reactions. And so typically we will, I'm saying typically a lot, I'm sorry. We are going to have your reactants and we have to use a double displacement to figure out what's going on. But the additional thing on top of that is figuring out what is the fate. Is it going to be a liquid? Is it going to be a solid? That's a little extra tidbit that we're building off of. Here we have writing equations. Remember double displacement. You have a cation and an anion for all of these metal, non-metal components. So C plus and D minus. It's important when you do double displacement that you add the cation from one compound and the anion from the second. So the A and D, I have a plus and a minus together. And then you have the cation from the second compound and the anion from the first. So you have to flip it, but you don't do cation, cation, anion, anion. You have to do positive and negatives. And that's how double displacements work. And then we always start with the cation, the positives go first. Even though here it's BC, you always have to flip it because you have the C plus first. All right. I like this. This is fun because it's really going to challenge everything we've learned so far because we have to figure out what is going on the other side. So it's lead 2 nitrate reacting with potassium iodide and include the phase and subscripts. Okay. This is a double displacement reaction. So I have lead. Lead is not one of those set metals, but they gave us the charge. It's 2+. And I have NO3-. Okay. Then I have K+ and I-. So that double displacement, the plus here is going to combine with the I here. So the Pb 2+ combines with the I. So now I have and I have to remember to do the crisscross method. So that gives me PBI2. The next one we have to do is the plus from the second one has to combine with the negative from the first. And luckily, I don't have to do the crisscross method. All right, so we are good. Everything is good. We just got to double check and make sure everything is balanced, and then we will do the phases. Let me clean it up. Sorry, let me know if you need me to put anything back up here. All right, next, let's balance. I have lead. Keep the nitrate together. I have 1 lead here, 1 lead here. I have 2 nitrates here, 1 nitrate here. I have 1 and 1 iodide. I have 1 and 2. So the first thing I think I need to do is I would like to get the nitrates balanced. So I'll put a 2 out front here and here. And now my potassium's not balanced. So I'll put a 2 in front of the potassium, and that gives me, and now it's balanced. Last step, because we've already kind of done all this. We need to figure out what are the phases. So lead iodide. If I go to my solubility list and I find iodide, I think it's going to be under halogens. Yeah, halide ions. Look at halide ions. They are almost always soluble with the exception of what metals? Silver, mercury, lead. So even though they are almost always soluble, lead is the exception to that rule, which means lead will be a solid here. And then potassium nitrate, nitrates are soluble with everything. So I am not going to put a solid because it's going to dissolve. It's soluble. So I'll put an aqueous to tell us it's in a liquid state, it's dissolved in water. So we literally just built off of everything. We did balancing in unit 1.7, but now we did the double displacement using our ions, and we did all of it. Double displacement, balance, and then with the solubility rules, we were able to identify the phases. These are really good practice, and I have several of them in your homeworks. Are there any questions on this? All right, I want to show you all the homework. Hopefully, with our little bit leftover time, we do some of the homeworks. This isn't, if you find 2.2, I like this, I love this question. The video shows the addition of aqueous sodium bromide to a solution of aqueous silver nitrate. Watch what happens. it's precipitating out, right? So there's a solid forming. I don't know which one it's going to be. It says write the balanced molecular equation for the reaction and include phases. So first, if you want to get your homework out and do this with me, because everyone will be given like different things. But I'd love for us to like kind of go through these problems together in the time. Write the balanced molecular equation for this reaction, include phases. So it says aqueous sodium bromide. What does that look like? Yep, NaBr. But it wants phases, so I'll do aqueous. I don't need to do crisscross method here because sodium's a +1 charge, bromide's a -1, so I'm leaving it as NaBr. So aqueous sodium bromide plus aqueous silver nitrate. So Ag for silver, and then NO3 for nitrate. And I also don't need to do crisscross method here because they're +1 -1. Let us, I do that? No, here, sorry. All right, now we need to figure out what's on the other side of things using double displacement. So first, start with the cation here, sodium. What is it going to be on the other side? So sodium's going to be with what? Nitrate, because I'm flipping them, right? Okay. And I'll do the phases in a little bit. What is the other component? Now let's do phases. I don't need to balance anything because everything's like the same charges. And if I go and check again, I have one sodium on both sides. I have one bromine. I have one silver, one nitrate. So it's already balanced. Sometimes you'll have to do those extra steps, but in this case, we're good. Nitrate. Why is it aqueous? Mm-hmm. All right, so what is the silver bromide? Look under halide, halide on it. Yep. Oh, this would be solid because they're always soluble except when it's silver bromide.
Oh, that makes it.
Yeah, and also deduction. If I know sodium nitrate will always be aqueous and I go back to this video, that means the only thing left over has to be the solid. Like if this video showed no precipitate, then both would be aqueous. Check. Oh, he did it. Good job. All right. Let's do this next one. Where's the video? I like videos. Okay. This video shows the addition of aqueous sodium carbonate in a solution of aqueous iron nitrate. So sodium carbonate, it's like kind of foggy, I don't know. But when you add something in, you have definite solid forming. Let's write it all out. Aqueous sodium carbonate. What is, so sodium is a +1 charge. Does anyone remember what the charge of a carbonate is? Two minus, yes. So in this case, for this to be balanced, that sodium needs to have two of them if I did the crisscross method. So I'll do Na2, CO3, and it's saying it's aqueous. So I'll add the aqueous. And then it says iron nitrate, and it's iron 2 charged. So that means that you have Fe and then you have NO3 minus. So Fe2 plus NO3 minus, crisscross them, and you have Fe NO3 2. and it's also aqueous. All right, so let's do the displacement, double displacement. What is sodium going to combine with? Question. Aqueous or solid? Yes. Okay, and what is the next one? Yes. And this one does not need crisscross because you have Fe2 plus and CO3 2 minus. Okay, carbonates are insoluble with everything, but iron is not on the exceptions to that rule. So this is going to be solid or aqueous. The last step here is let's double check and make sure it's balanced. So I have 2 sodiums here on the left. I'm going to have to put a 2 in front of the sodiums on the right. Okay, that makes, now I have my nitrates balanced too. So I have 2 nitrates and 2 sodiums. I have 1 carbonate and then 1 iron. So just adding this 2 balances it. Oh, it's saying it's wrong. What did we get wrong? Na2, CO3. That is correct. Yeah. Sorry, I'm not used to doing homeworks through this platform. Yeah. Where do you do try again? Oh, try again here. Aqueous sodium carbonate. That's correct. To a solution of aqueous iron nitrate. That's correct. These spaces? Or does it want like these flip-flopped? Hint? We did that. Nope, I don't want to do that. I don't get it. We did it right. This is correct. Let's flip-flop them. Oh, I put a 2 up front. That does not need a 2. 2. Oh. 3. Write the balance net ionic. Oh, fudge. Net ionic equation. We didn't cover this one, so I'm going to take this one out. Net ionic equation for this reaction include phases. I believe this one wants charges. Yeah, I'm going to take this one out because this one would be if I broke it completely up into ions. I'm just going to skip that one. Okay. So sodium nitrate and sodium chloride, and look how nothing is happening. Write a balanced net. I'm gonna take this one out too because I don't like net ionic equations. Okay, this one's better. Sodium nitrate and sodium chloride. It shouldn't have anything happen because so soluble and soluble create soluble and soluble. So if there's nothing happening, it's just creating 2 different solubles. So classify each reaction according to other precipitate forms. Copper nitrate. Ooh, this is a good one. So copper nitrate, so does copper sulfate, is that one precipitate form for copper sulfate? Copper sulfate. No, precipitate will not form. Magnesium hydroxide would precipitate form. No, I don't think so. It says it's insoluble except, no, it would. Magnesium hydroxide would form precipitate. Okay, silver chloride, definitely precipitate. Magnesium.
Just in your head, are you
I'm flipping them in my head.
Later.
If you, yeah, I'm doing the double displacement in my head, but I highly recommend like y'all do it written out while you're learning. So what I did here was you have silver will combine with chloride. I know that sodium nitrate will not create a precipitate, but silver chloride will. Magnesium will combine with OH, and that will create a precipitate because under hydroxides, it's magnesium is not a level 1 or a column 1. And I can ignore the sodium nitrate because sodium nitrate is soluble. Copper sulfate. If I go under sulfates, they are soluble with the exception, and copper is not one of them. All right, so I have magnesium bromide. So under halides, is magnesium bromide going to dissolve? Yes, I agree. So it does not form. What about iron hydroxide? So precipitate will form. What about sodium bromide? What about sodium nitrate? So anything with a nitrate will be soluble, right? Okay. Lead sulfide. Mm-hmm.
Oh.
Yeah, we did it.
So those really only have to look at like the first.
Because the second one, like anything sodium mixed with nitrates, which most of them are sodium nitrates, I kind of can ignore because they're always soluble. But the way that you do this is you want to break it up. I would probably put it on my notes. I would do the displacement, see what, and then I would use this. So I can do it in my head because I've done it so many times, but as I'm learning, I would write it out in my notes as much as possible. I could also do it on the board behind me too. So, oh yeah, here's a good one. Complete the solubility table. So if I mix sodium and bromide, soluble or insoluble? Silver bromide. Calcium bromide. Iron bromide. So let me double check. So bromide combined with silver, mercury, or lead are insoluble. So iron would be soluble. It just takes a little.
Yeah.
All right, let's practice hydroxides. Sodium hydroxide. Silver hydroxide. Calcium hydroxide. Iron hydroxide. Let's do perchlorate. Sodium perchlorate. Should I just, okay, I was deciding for this one, it says there are no exceptions, so I can do soluble across the board. Phosphates, let's do sodium phosphate. So it says when combined with alkali metals, it can be soluble. So I'll put soluble. Silver phosphate. All right, yeah, so insoluble, let me do this real quick. Insoluble, calcium phosphate, insoluble, insoluble. Let's check. Yay. Yeah, so I'm gonna take out these problems and I'll double check the rest of them. If it says net ionic, I don't want y'all doing that yet. But this is still correct. We still got it right. But yeah, if you can, start going through those homeworks and getting all of the second one, 2.1 and 2.2 done. Do y'all have any questions?
So that last row we were just going over, combining with alkali metals, that's just gonna be the first,
The first
Row.
column, yeah,
doesn't include the second one, the alkaline earth metals.
no, just the first one. Okay, I can see why it's, like, if you want to make a note on the side, that alkali earth metals are including these. Or lithium all the way to francium.